Today I'm going to talk about how to break the Rabin encryption system when we don't use any randomization during encryption. Okay. So we talked about the plain Rabin encryption earlier. I will quickly summarize what it is. Suppose you would like to encrypt a message M. All you do is you take M square and compute the M square mod N. Okay. If N is the public modulus, let's call N as the public modulus, right? What is N? N is made of P and Q, two primes, more or less same size. Usually N is a 2048-bit number or so, or above, okay? All right, so P and Q are both equal size primes. The difficulty is given N, it is not easy to find P and Q, okay? So in the Rabin encryption scheme, we take a message M, we compute M square mod N, and we send this C to the recipient. The recipient, if he or she knows the prime factors of N, he can reconstruct M. Attacker cannot reconstruct M because we don't know how to find the square root of C without knowing the prime factors P and Q. There are actually 4 roots to this problem. We can find all the 4 roots if you know the prime factors P and Q. And the message must have some redundancy, otherwise the receiver wouldn't know which message to pick up, okay? Something like a message header or something like that. Anyway, so the problem is simple, right? How do we find the root C? The answer is we don't know how to find root C. So what I'm going to talk about is a slightly different scenario. The scenario is like this. Suppose you have Alice, right? She wants to talk to 2 people, say Bob and Charlie, okay? So what Bob will do is he will publish his public key, the number N, to the world. I'm going to use N1 as Bob's public key, N2 as Charlie's public key, right? So the problem now is Alice is going to encrypt, say, let's assume for some reason she needs to encrypt the same message to both people. So her encryption will look like this, right? She takes the message M, she computes M square, let me write it this way. She sends to Bob M square mod N1, right? That's how the Rabin encryption scheme is defined. Okay, N1 is made of P and Q, right? Let me call it P1, Q1, just to avoid any confusion. Both are primes of equal length, and the N2 is P2, N2, okay? By definition, in this context, let's say the same message M is encrypted to Charlie. Alice will be sending M square, but mod N2 because N2 is the public key of Charles. Okay, so now the problem is easy to solve. We can find the value of M using Chinese remainder theorem, which we talked about it earlier. The reason why it's possible to solve using Chinese remainder theorem is the following, right? Chinese remainder theorem has this nice property that suppose you would like to find out X mod N1, N2, right, into N2. Okay, I'm going to make some assumptions now. Usually N1 and N2, the GCD is 1. We are randomly picking the numbers, therefore it's safe to assume, otherwise the whole thing is already broken, right? If GCD is not 1, you have already found out the prime factors. Okay, so we assume this. So in that context, what we are going to do is we're going to apply Chinese remainder theorem, which says that more generally, given a number X in N1, N2, N1 times N2, we can map it to first group, right, N1, X mod N2. So we given a point in one group, we can map it to the other 2 groups, right? This is one group. Let's call it Z N1, N2 group for a moment, right? Set of all integers from 0 all the way to N1 times N2 minus 1, and that's the meaning of Zn. The same thing here, right? Zn1 and Zn2. Okay, all right. So what is the reason I'm bringing Chinese remainder theorem is that from this problem, we can easily see that this is public data, right? M square mod N1 is a public data. M square mod N2 is public data. We don't know M, of course. outputs. That's what we need to find. Let's call this constant C1 and let's call this C2. Okay, what are the things now we know? We do know, let me change this notation a little bit. Okay, that may be better. I think we can just keep it as X or M, doesn't matter. M is the message, let's call it. M is the message you would like to find out, right? So in this case, it's M square, right? So we need to find M square. So what we can do is, what are the things we do know so far? We know this is public because it's sent over the wire. Okay, but this is nothing but C1. This is nothing but C2. Okay. The Chinese remainder theorem just takes this component, this first component, the second component, and the public components N1 and N2. So there are 4 components to the Chinese remainder theorem, right? This is the third component, and this is the fourth component. It will give us as output. What will it give us? The output. The output it will give us is the right hand side, M square mod N1 N2. So what can we do with that M square mod N1 N2? Our goal is to find M, right? Well, let's think about this. What is the mathematical relationship between M and N1? We do know that M has to be below N1, right? Because it's coming from the, otherwise you cannot even apply encryption. M has to be an element below N1. And the same with the M has to be below N2, okay? In fact, M has to be smaller than the minimum of N1 and N2, right? Otherwise, we cannot apply this scheme on Rabin encryption scheme, okay? Otherwise, we cannot encrypt the message M on the Rabin encryption scheme, okay? So we do know that M has to be smaller than M1 and M2, okay? All right, so now, which means M square mod N1 N2 is nothing but M square, right? Because M square doesn't wrap around when you do mod N1 and N2. Given the fact that M is less than N1, M is less than N2 implies M is less than N1 N2, okay? So M square is less than N1 N2, which means when you do mod, it doesn't wrap around. Therefore, we can just say, by applying the Chinese remainder theorem, we directly learned M square, okay? Which means we can just take the square root of M square, we get the message M. I hope this is clear. Let me explain this one more time, just to be sure. Alice wants to send a message M to Bob. She also wants to send the same message M to Charlie. Of course, both Bob and Charlie, they have their own public keys, right? Here we are using the plain Rabin encryption scheme. Plain Rabin encryption scheme means the message is not padded, there's no randomization, whatnot, right? That's the plain or raw Rabin, okay? Although we don't know how to find a square root in the modular arithmetic context, but we have 2 equations here. This is the first equation, second equation. We can apply Chinese remainder theorem to find the M square automatically. We talked about Chinese remainder theorem earlier, so I recommend you to watch those videos or refer other videos. So we do know M square mod N1 send over the wire. So eavesdropper Eve can look at this one and this one. That's not a problem. By applying Chinese remainder theorem on all the public components, we can reconstruct M square in Z 1 times Z2 group, okay? But we know that M is smaller than N1, M is smaller than N2, therefore M square must be smaller than N1 times N2, right? And therefore, when you do modular arithmetic, when this number is smaller than this number, right? There is no reason for mod at all, right? It's like 5 mod 6, which is 5. So what you get out is root of, what you get out from Chinese remainder theorem is M square. And we just take integer square root to get M. Okay, that's the idea. So let me show you a quick demo in Python. Okay, so I'm not going to talk about all the details, but the most important ones I will talk about, right? Here is our encryption scheme, which is basically the message that you would like to encrypt. N is the public modulus. All we are doing is A square M. We call this M as a message. This is basically what you saw on the slide, okay, on the whiteboard. Okay, so N is the public key. So we can now go to the main. Don't worry about this recursion limit because I was doing some recursive calls earlier, we can remove that. First thing Bob is doing is Bob is generating his public key, right? And of course sends only N1 to Alice and keeps P1, Q1 private. Charlie does the same. He generates his private public private key pairs and sends N2 to Alice. Alice encrypts using Bob's key, the public key, right? And that's the reason why you see N1. Let's say in this case we are generating a random 500-bit data to encrypt, and Alice is also going to encrypt the same data. This is the same data using Charlie's key. That's why she's using N2. And now we apply Chinese reminder theorem on all the public components. C1 is public because it's output of encryption function. C2 is also public, output of encryption function. N1 is public key, N2 is another public key, and we multiply N1 and N2, it's public, of course. And all we are doing is, after we are done with the Chinese reminder theorem, we check that the Chinese reminder theorem output is nothing but the square of the data, or the square of the message. And then we take the square root of the message, which is coming from Chinese reminder theorem. We assert that that is nothing but the data we encrypt. Okay, we can just put an assert. If there is something wrong, it will fail, right? The assert will fail. Let's run it now. Yeah, there's no problem. Let me just put a bug. Now it should fail. Yeah, you see it fails. That means the Chinese reminder theorem is able to find m square, and then because m square is smaller than n1, n2, we can just take the square root of m square to get the message. Okay, the data is the message m that we talked about on the whiteboard. Okay, so that's basically it. Of course, 512 is a small key size for demo purpose. You should be using 20, 48, whatnot. Just a piece of warning. You have to make sure that whenever you use Rabin, don't use the raw encryption scheme that I just talked about. Rabin also has a randomized version, which I talked about in other videos. Okay. Otherwise, you will get into this Chinese reminder theorem based attack to break the scheme. It's going to generate 2048-bit key, and I'm going to wait for a few seconds. So I'm doing it using an online Python version, so it's a little slow. Okay, so now Bob's key is generated, Alice's key is being generated now. Of course, this is done only once. It's a little slow because I also implemented my own Rabin Miller algorithm, so it's taking a little time. It's not necessarily optimized, just for experimental purpose. Okay, so Charlie's key is also generated. Now Alice is going to encrypt some data using Bob's key, public key, and that's the next step. And assertion all succeeded. Otherwise, we would have gotten a failure here. Okay, so that's basically it. So the key message is that we should never be using an encryption scheme that has no randomization. Okay, when you encrypt the message m, again you get the same ciphertext. In this case, same message is sent to two different people. Although we don't know how to solve this equation, right? We don't know how to solve this equation. If n is a composite number, given c and n, we don't know how to find m. Okay, given c and n, find an m. We don't know how to do that. However, the problem we solved is slightly different. We solved this problem. Given c1 mod n1, right, and mod n2, we found a way to find use the Chinese reminder theorem to find m square, right? And then we just took square root of m square, which is nothing but m. Okay, this is no modulus. That's the reason why we can apply regular square root. The reason is that m is less than n1, m is less than n2. Therefore, m square mod m1, m2 mod n1, n2 rather is nothing but m square. This is because m square is less than n1 times n2, which means that the Chinese remainder theorem gave us this. We just take the output of the Chinese remainder theorem, so and take a square root of the output of Chinese remainder theorem. That's basically what we did to find the value of m. M is the message, secret message we would like to extract from public data C1, C2, N1, N2. Of course, N1 is made of 2 primes P1 and Q1 of equal length, and so is N2 P2, Q2 of equal length. Okay. All right. This is pretty interesting. That Chinese remainder theorem is useful for attacking systems that do not have randomization. If the message is randomized, then we can't apply Chinese remainder theorem. Okay. All right. That's all.